So for problem number 23, it says use table 1-3 to estimate the total number of protons or neutrons in a bacterium, a DNA molecule, the human body, and our galaxy. And so what I notice about this chart is the commonality of all these objects is the mass. In other words, that's the unit that they have together. So I'm basically going to use conversion factors to cancel out to where I get something compared to the other thing, okay? So I start with 10 to the negative 15 grams is equal to 1 bacterium. Then I want to cancel out the grams because I want to figure out how many protons are in a bacterium. So I want to cancel out the grams. So I write 10 to the negative 27 kilograms on the bottom, not grams, kilograms, is equal to 1 proton or neutron. Well, that's easy. So what happens here is because I wrote those two ratios that way, the kilograms cancel. And essentially, I end up with 10 to the negative 15 protons or neutrons to 10 to the negative 27 bacteria. Now I'm going to do a little math. I'm going to add 27 to this and add 27 to this. And so I actually get 10 to the positive 12. What the heck is that? My little pen thingy here is not cooperating with me. 10 to the 12 protons or neutrons per 1 bacterium. So now you could think of that as 1 bacterium is equal to 10 to the 12 protons or neutrons because they're similar in mass, roughly, according to the orders of magnitude. And so that's all we got to do for each one of these. So on the next one, if I do DNA, I'm going to start with the mass of the DNA. So I'm going to go down here. This is the mass of the DNA. And I'm just going to say 10 to the negative 17 kilograms is the mass of 1 DNA molecule times, and this last part should be the same for all of these. So it's just going to be 10 to the negative 27 kilograms is how much 1 proton or neutron weighs approximately according to the orders of magnitude. What cancels? The kilograms. And so I'm left with 10 to the negative 17 protons / neutrons is equal to 10 to the negative 27 DNA molecules. And so I'm going to add 27 to this and add 27 to that. So when I do that, this becomes 10, right? So then my final answer is 10 to the 10th power protons / neutrons per 1 DNA molecule. In other words, 1 DNA molecule has 10 to the 10 protons or neutrons. Let's do the next one. The next one was the human body. Now, they don't have it in the thing there, but what do you think the average human body weighs? About 100 kilograms. So we would say 10 to the 2 kilograms. Actually, that's kind of high. To 1 human body. What do I put on the next thing? 1 proton / neutron weighs 10 to the negative 27 kilograms. The kilograms cancel. And I'm left with 10 to the positive 2 proton / neutrons all over 10 to the negative 27 human bodies. I'm going to add 27 to both sides. This becomes 0. When I add 27 to 2, this becomes 29. In other words, a human body has 10 to the 29 protons or neutrons. That's a lot. Okay. And I'm not going to crank through the math, but the galaxy, they do have the human body listed in the list. The galaxy, if you crank through and you do the same math, the galaxy, the ratio is 10 to the 68 protons / neutrons to one galaxy. Yeah, but I'm not going to do all the math. I kind of ran out of room. But yes, you would plug in 41, and then when you add 27 to the 41, you would end up with 10 to the 68. Okay? Are there any questions on that one? That was a good one.